Hi everyone, I think we are live, so there's still 15 seconds pending, so let's wait for it to end. Okay. Uh, Quickly, let me know if you guys can hear me properly. I think I'm audible. So hi everyone, and yep. So today we'll be discussing the problems that you actually had in the interview series for Swiggy. Uh, yep. Let me know what was like. How did you like the problems? Were you able to solve both the problems? Did you get stuck in any problem, or how did you like the questions? Were they good? Were they not that good, or something like? Let me know your experience. Thanks, Ankit, for clearing it out. Yeah, let me know about your experience about how did the contest go, and what do you feel can be improved versus like how did you like the questions, everything. Second one was easy. Okay. Second one means binary matrix, right? So binary matrix was easy. The problems were good, but I got stuck. What is happening here? Uh-huh. What is happening? Okay, I was in a magnifier. uh both problems solved. Awesome. Solved only second one. If the questions were easy. Okay, okay, okay. Yep. Then it looks like, is there any track of this interview series contest participation in GFG? uh I'm not sure. Maybe in your profile you can see something. I'm not sure about that. If someone knows about that, like if there is a track about how many contests you have participated in and what are these ranks and everything, you can let me know, so that others, it can help others, right? uh, Okay, okay, got it. So let's discuss without wasting time. Let's actually discuss. I think most of you are here, so let's understand the questions and try understanding how to solve them. Right. So the first question is minimize the sum. So the question is basically you are given n elements, right? You are given n elements. You can remove any two elements from the list, note their sum, and add the sum to the list. So you are given n elements. At every move you just take two elements out from the list, you remove them from the list, you add them up, and then you add the result back to the list, right? And repeat this step while there is more than a single element left in the list. So you have to repeat this continuously. When does this stop? When you have only one element, because when you have one element you cannot take two elements, right? So you will stop when there is one element left in the list. The task is to minimize the sum of the chosen sums. Minimize the sum of these chosen sums. Does this mean? So at every move you are removing two elements, you are adding them up, right? So you get some sum. After the next, in the next move you again get some sum, like that. So you have to minimize the total. Like when you add these sums up, like when you are choosing two elements and you get the sum, you add these sums up, the result that you get, you have to minimize that, right? For example, 1 4 7 10, 1 4 7 10. What's happening here is, you can choose in the first move, you can choose 1 and 4. So let's actually draw this. So 1 4 7 10, right? We'll understand everything. They will just wait for some time. 1 4 7 10. first move, what we can do is we can choose 1 4. So what is 1 plus 4? 1 plus 4 equals to 5. So keep this separate, like track it in answer. So let's say answer plus equals to 5, so answer becomes 5. Now you insert 5 back to this list. So what does it become? It becomes 5 7 10. Now what do? You choose 5 and 7, let's say. So 5 7, what do you get? 5 plus 7, 12, right? So you get 12, so answer plus 12. So you insert 12 back to the list and you choose 12 10 together, that is 12 plus 10, 22. You add this to your answer, so answer plus 22, and you add 22 back to the list, right? So what do you get? 22 plus 12, 34, 34 plus 5, 39. So 39 is the answer. 39 is the answer. So you have to minimize this, and this is the minimum possible, right? This is the minimum possible. Why is this the minimum possible? Or you can tell that there is always one answer. How do we disprove that? So let's just take this 1 4 7 10 only, right? 1 4 7 10. Let's say instead of 1 and 4, let's take 7 and 10 in the first move. So 7 plus 10, it becomes 17. So answer becomes 17 in the first move. And what do you have? You have 1 4 17, right? Let's say you choose 1 and 4 now. So 1 plus 4 equals to 5. So answer plus 5, this sum, and you insert 5 into the list, 5 and 17. So 17 plus 5, now you choose, and you get what? 22. So insert 22 back and plus 22. So in this case, what is the value that you get? 22 plus 5, 27, 27 plus 17, 37, 44. So 44, right? So basically the way you are choosing, you get different results, right? Based on the way, based on the numbers that you're choosing, you get different results. We can see that you have to find what is the minimum. So we got 39 in one move, and that was the minimum possible, right? So this is the question. I hope the question is clear with everyone. Let me know if you have any doubt with the question. Let's now try to move to the solution. Okay, so how do we minimize the sum? So what are we essentially doing is we are doing answer plus equals to AI plus AJ. We are choosing AI AJ, and we are doing answer plus equals to AI plus AJ. Let's say we have three numbers. Let's just think simply, right? We have three numbers. Let's say 2, 4, 6. What should be the way we should choose the numbers? That is what we have to determine, so that this answer becomes minimized. This answer is minimized. If you notice carefully, it is always in the best interest for us if we choose the minimum two numbers and add them up. It's always better for us if we choose the minimum two numbers. Just think about the first move. In the first move, we can choose 2 and 4. So 2 and 4, we get 6. Or we can choose 4 and 6, we get 10. Or we can choose 6 and 2, we get 8. So which one gives the minimum one? Which one gives the minimum one? 6, right? 6 gives the minimum one. In the next, so at every move, we get, so we, what is our answer? Our answer is summation over all such pairs that we are choosing, right? AI plus AJ. Summation over all such pairs that we are choosing, AI plus AJ. So we can, for every move, if we minimize this, if we minimize for every move, we minimize what is the sum that we get. And in fact, like you are inserting 6 back to the list. Here you are inserting 10. So you are inserting bigger numbers into the list as well. Just think about that. You are inserting bigger numbers into the list. So it's always in our best interest to minimize. We have to minimize the total sum, right? The total answer. So why not we minimize every move? We try to minimize every move. So how do we minimize every move? We see clearly that if we choose the smallest two numbers, we minimize every move, right? So the problem now becomes very simple. At every step, we have to choose minimum two numbers. So what has the problem reduced to? At every step, choose minimum two numbers. Now you can definitely think in terms of sorting, that you would just sort and you would take you would take them from left to right, but again that would not work. Why? Let's just understand with an example. Let's say we have something like 2, 4 5 7. Okay, yes, 2 4 5 7. After the first move, what do we combine? 2 and 4. Now if we sort them and do them in a sequential order, what do we get is first move 2 4, it becomes 6, answer becomes 6 firstly, 6 5 7, right? 6 5 7, and actually let's have one more value here, 5 5. Let's have two fives here, right? 5 5 7, something like that. 5 5 7. So we have 6 5 5 7. In the next move, we would actually, if we are just sorting and doing it in this way, we would have chosen 6 5. But again, the best, like, again, just think about this situation. What are the various possibilities? 6 plus 5, that is 11, or 5 plus 5, that is 10, or 5 plus 7, that is 12, or 6 plus 7, that is 13. So 10 is a better alternative, right? So at every move, we have to choose the minimum 2. And the list that we have, that is dynamic, that is we are adding that to the list, and in a dynamic way we need to update the minimum as well. So definitely sorting won't work. Sorting would just sort the initial list, but after that, once you have 6, you would have to resort it again. हिंदी में बता दो, हिंदी में ठीक है बता देते हैं. तो लॉजिक ऐसा है कि मान लो तुमको करना है मिनिमाइज, राइट? यू हैव टू मिनिमाइज द टोटल सम. व्हाट हमको क्या पता चला कि अगर हम लोग एवरी मूव पे मिनिमाइज करते हैं, हम लोग को एवरी मूव पे मिनिमाइज करना होगा. हाउ डू वी मिनिमाइज एट एवरी मूव? जो दो छोटा नंबर्स है, द स्मॉलेस्ट 2 नंबर्स, हम लोग हमेशा वही चूज करेंगे जो स्मॉलेस्ट 2 नंबर्स है, राइट? yes, insert at correct position so that resulting, yes, you have to insert. So ठीक है, उस पर आते रुको एक सेकंड, मैं बता देता हूँ. सो हमको हमेशा 2 छोटा नंबर चूज करना पड़ेगा, जो स्मॉलेस्ट 2 नंबर्स है एरे पे. at any point of time we have to choose them and add them up, and that would actually minimize our answer. बट अगर तुम ऐसे सोचते हो ठीक है हमको छोटा नंबर चाहिए तो हम सॉर्ट कर लेते हैं, तो हम लोग वही डिस्कस करें कि सॉर्टिंग से क्यों नहीं होगा. सॉर्टिंग से इसीलिए नहीं होगा क्योंकि मान लो तुम्हारे पास एरे ऐसा है 2 4 5 5 7, ये सॉर्टेड है, तो तुम लेफ्ट टू राइट ट्रेवर्स कर रहे हो. आफ्टर द फर्स्ट मूव तुम्हारा क्या होगा? 4 + 2 6 बन जाएगा, तो एरे बन जाएगा 6 5 5 7. ये लेकिन सॉर्टेड नहीं है, तो हम लोग अगर 6 5 को कंबाइन करते हैं, दैट वुड बी अ बैड मूव. वो गलत मूव होगा क्योंकि 5 5 गिव्स अस अ बेटर रिजल्ट, दैट इज 10. सो वी शुड कंबाइन 5 5. तो आफ्टर एवरी इंसर्शन वी शुड हैव द एरे सॉर्टेड. तो मतलब मान लो कि तुम इधर से 6 जनरेट हुआ, so what you are doing is you are inserting 6, so you should keep it sorted. So it should become like this 6 7, right? It should become like this 5 5 6 7. So definitely if you are sorting after every move, that will make the complexity worse, right? After every move if you are sorting, it will make the complexity worse. So we need to do it in an intelligent way. Is there a data structure? Now let's think about this. Is there a data structure that allows us to get the minimum element? Also allows us to add elements to it dynamically and remove the minimum element. That's what we are doing, right? We are removing the minimum element, we are getting the minimum element, and we are adding element to the list dynamically. Is there a data structure that can handle all 3 of them? कोई data structure है क्या जो handle कर पाएगा removing the minimum element? So what do we need? Let's think about it again. What are the functions that we need? First is getting minimum element. Second is removing minimum element, because हम लोग minimum और second minimum को remove करेंगे, तो 2 बार अगर remove करते हैं तो minimum and second minimum will get removed. So removing minimum element. The third operation is insert element. So is there a data structure that supports all 3 of them together? Is there a data structure that supports? Yes, exactly. Min heap is a data structure, or a priority queue is a data structure that can support all this, right? A min priority queue or a min heap is a data structure that can support all of these. So abhi logic simple ban gaya. The logic is simple now. We have to maintain a min heap or a priority queue. We will we'll add all the elements to the priority queue. At every step we will remove the minimum 2 elements, we will add them up and add it to our answer, and we'll add their summation back to the priority queue or the min heap. So that's the logic, and that would give us the minimum answer always. because we are minimizing every move. So let's look into the code for this. So what we'll do, we'll create a priority queue first. Priority queue int. Now how do you create a min priority queue? Normally max priority queue hota hai. If you just create a priority queue, it will be a max priority queue or a max heap. So to create a min priority queue, you can do it like this: vector int, and third is the comparator, that is greater int, right? So this will create a min priority queue, or this will create a min heap, right? So this creates a min heap. Let me see if I can write. Okay. So first of all, we'll enter all the elements. नहीं issue हो रहा है थोड़ा. Okay. For int I equals to 0, I less than n, I plus plus, will insert all the elements to the priority queue. So pq dot push, I think push is there, push ARR of I. Now we'll have the answer. What do we do at every step? While pq dot size is greater than 1, in tp equals to pq dot top, will take the first min. Let's call it first min. pq dot top, pq dot pop will remove the first min, right? We'll take the second min now. pq dot top again, and we'll remove it, pq dot pop. And what we'll do, answer plus equals to first min plus second min. Let me give some spaces. Okay, answer plus equals to first min plus second min. And what else we'll do, we'll add that to the pq. So pq dot insert first min plus second min, we'll add the result back to the priority queue. So like this we can do, and we'll get the minimum element at after every step. So our answer will be return answer, right? Return answer. So let's compile and run this. Anyone has any doubts with the logic? Anyone has any pq dot insert push hoga? Anyone has any doubt with the logic or the code that we have written here? So any doubts with the code, any doubt with the logic that we're using? So it's working. I'll just increase the font size so that you can see clearly. Any doubt with the code? Any doubt with the logic? Or is it clear? Can you let me know in the chat? Any doubt with the code or the logic? Please let me know in the chat. Please show how your code. Okay, let's do that. So let's try to run this on the list of elements. Okay, let's try to do that. Okay, let's do that. I'm unable to open some. Okay, so let's say we have what do we have? We have, let's say, let's take the example that we were talking about, right? So we have 2 4 5 5 7, 2 4 5 5 7, right? So we'll insert that in the priority queue. So let's just assume that this is the priority queue right now. Now first of all, we'll take the first minimum. First min becomes what? First min. So let's write it down here only. First min becomes, first min will become 2, right? First min will be pq dot top. At the top we have 2. So it will be 2 at the top. Then we will remove this. So this gets removed from the priority queue. So this is removed from the priority queue. Now we have again second min is pq dot top. What is pq dot top now? 4. So this will become 4. And then it is removed again, right? Pq dot pop. So 4 is removed from the priority queue. Answer plus equals to, so answer equals to what right now? First min plus second min, that is 2 plus 4, that is 6. And we'll pq dot push first min plus second min, so we'll push 6 into the priority queue. So when we push 6 into the priority queue, the order will be like this: 5 5 6 7. Now the size is greater than 1, right? So we'll again start. So pq dot pop, first min is obtained, so 5 is taken out, so first min becomes 5. Again pq dot top and pop, 5 is again taken out. So answer plus equals to 5 first min plus second min, that is 10. And we'll insert 10 into the priority queue. So 10 is inserted, so it will look like this: 10 6 7 10, right? Okay, now first min will be 6 and 6 is removed from the priority queue. The second min will be 7 and 7 is removed from the priority queue. So what is 6 plus 7? 6 plus 7 is 13, I believe. So plus 13, and we'll insert 13 into the priority queue. So it will become 10 and 13. 10 and 13, right? And finally we have 10. So 10 is obtained here, 13 is obtained here. We'll remove both of them and we'll insert 23, and 23 is inserted and plus 23 to the answer. So we get the answer to overall answer, which is 23 plus 13 plus 10, that is 36 46 52. 52 is the overall answer, and we get this, right? So this is the minimum possible value that can be happen, right? So we get 52. Is it clear now, Devapriya? Is the code clear how it is working? Does the code make sense? Let me know if it is clear. Okay, awesome. So I believe it is clear with everyone now how to solve this. So we'll move to the second problem. The second one, many of you already told that it was easy, but in Java you can get the code from the solutions, right? Just look into the editorial or something, and you will definitely get the code in Java as well. I'll be doing only in C++. Okay. This one, many of you already told that this is easy. Okay, many of you told actually this is easy. All that is easy, but if you look into this complexity, I'm pretty sure that most of you didn't meet this complexity, because there is no way to prevent n into n, right? There is no way to prevent n into n, so you just ran a n into n loop and you did the solution, right? So I'm pretty sure none of you actually made this complexity. Anyone made this complexity order of n and order of 1? Expected time complexity order of n, expected space order of 1, or was it n square, like the easy one? Just go through all the all the rows, find what is the number of ones, and then figure out the maximum and minimum. Anyone was able to do it in order of n and order of 1? Order of n time, order of 1 space, because it's not that trivial. Let me know anyone who's able to do this complexity or not. You were. Can you suggest your approach? Like, how did you do that? Can you tell? Can you share with us how did you do order of n, order of 1? then you are traversing, right? You are traversing all the elements. It's not order of n, order of 1. Sushmit, it's not order of n, order of 1. Just think about it. It's order of n square. You are traversing the entire matrix. So it's that's just two cases you are handling, right? The last one is not zero. Like there might be you are just handling the two cases if there are no ones and if there are no zeros. So if there are all zeros and if there are all ones, what about the remaining? Anyways, let's actually read the problem statement. I'm pretty sure that most of you have done it in order of n square. Yes, I'm pretty sure that most of you have done in order of n square, right? So let's actually discuss the optimal one. So the problem is pretty simple. You are given a binary matrix of zeros and ones. All the rows are sorted, right? This is very important. All the rows are sorted. We need to find the row number which contains the maximum number of ones. What we have to return is the row number which contains the maximum number of ones. In case there is a tie, you have to print the smaller row number. Second is row number of ones. Okay, second thing you have to return is number of ones. So these are the two things that you have to return. So row number is, for example, in this case, the first row has 1 the second row has 2 the third row has 0. So the row number is 1, which is the maximum number of ones, and the number of 1 count is 2. So you're returning 1 and 2, right? So it's pretty simple. Like when you think about it, you can just do a n squared solution, right? You can just go through all the elements, all the rows. You can count the number of ones in every row, and you can return that. That's definitely a solution, right? That's definitely a solution. But that's definitely a solution. It's not order of n, fun with food. That's definitely a solution, but it's not matching our constraint. That is order of n and order of 1. So we have to solve it in order of n and order of 1 time. We will build on order of n, order of 1 iteratively. Let's discuss some other better solutions. Now the array is sorted, right? The array is sorted whenever there is something sorted. So every row is sorted, right? And you have to count the number of ones. So how does the row looks? 0 0 1 1 0 1 1 1 0 0 0 1. Let's say it looks like this. So for every row, what you are doing is you travel through all the elements and you found the number of ones. But as it is sorted, can't you just apply binary search on every row? You are applying binary search on every row and you are figuring out what is the first index that has 1. Once you have that, you can definitely do n minus I, where I is the first index that has 1, right? You can do it for all rows and you can do find the minimum number, right? You can find the minimum number. So that complexity would become for every row you are doing. So there are n rows into, you are binary searching on the column. So log of n, because it's an n cross n matrix, although it's not an n cross n, we need one more actually row. So let's have one more row here. 0 0 1 1, let's say. Okay, so it's n cross n. This is clear with everyone how to easily get into n log n. We had a solution initially n squared, which was easy. From n squared we have dropped down to order of n log n. Is this clear with everyone? We can just binary search for every row. What is the first index where 1 is happening? Once we have this, we can just add, we can just have like n minus I ones. Essentially we need the first index where 1 is coming, right? Then we know that there are n minus I ones in that row. In that row there are n minus I ones, so we can just compare. So I believe this is very clear with everyone. How can we do this? N squared to n log n. Let me know if you have any doubts on this. Okay, now let's talk about the optimal solution, right? Let's talk about the optimal solution. If you think about it, binary search is actually not necessary. Why? Let's understand how we can do this. for the first row, we will manually find where we have the first index of 1. Where we have the first index of 1, that is this. We will manually find that for the first row, right? So we found out that the first index of 1 is here. For the subsequent rows, when we go to the second row, what do we want? We want to maximize the number of ones. So definitely this pointer should never move to the left again. It should only move to the right, because if you are moving to the left, you are essentially reducing the number of ones. So you have already got more number of ones. Why would you go back, right? Why would you make it lesser? You want the maximum number of ones. So definitely will not move it to the left. You will always move it to the right. So from the second row, what you will do is you will perform a check here. Is the previous element also 1? So current J is at this index. This one, it is 1, right? Previous is also 1. Yes, previous is also 1. So you can actually move this pointer to the previous index. Let's move to and now we see the previous column is 1. No, right? The previous cell is not 1. So we will stop it here. Now the pointer is here. The pointer only moves to the left. The pointer is only moving towards the left because we want to increase the number of ones. Let's come to the third position. In the third position, we see that we have a 0 here. So definitely the number of ones in the third row is less than the number of ones in the second row, because it is sorted. So the ones will only be on the right hand side, and we see that there is a 0 at this column. So all the ones are on the right hand side. So that means number of ones is lesser. So we will just skip this row completely. We move to the fourth row. In the fourth row also we see that here we have a 0. So again we know that definitely we don't have a 1 here. So that's why we'll just skip this row as well, because the number of ones will be lesser here. And finally we have the answer, that the answer is index 1, row number 1, and the number of ones is 3. Right? So let's actually take another example just to understand better. So let's have 0, 0, 0, 1. Then we have 0, 0, 0, 0. Then we have 0, 0, 0, 1, 1, 1. Then we have 1, 1, 1, 1. So this is the array on which we'll do, right? So I think this will make much more the logic much clearer, right? So we'll start with the first row. First row will manually find what is the first column where there is 1. So we find it here. We'll move to the second row. In the second row, we see that for this column we have a 0. So we know, yes, we will know here only that number of ones in this row is definitely less than the minimum that we have the maximum that we have obtained. So we will just skip this row. Now in this row we see that we have this one as 1. Is the previous one 1 as well? Yes, it is. So we will move our pointer here and we'll update our answer. Our answer, like row, currently will become 2. Initially it was 0, now it will become 2 because here is 1. Again we see, is the previous one 1 as well? Yes. So the previous one is 1, so we'll move it to here as well. We'll move it to here. Now we see, is the previous one 1? No, it is not. So we'll update our answer. Our answer, number of ones, that is number of ones, let's call it. Number of ones becomes 3. Right? So we move to the next row. In the next row we see that this index is 1. So definitely the number of ones is same or more. Is the previous one 1 as well? Yes. So we will move it forward and we see that this is 1. So it is updated to row number 3 and the number of ones becomes 4. Right? And we are done. So we'll move to the last one and we are done, right? So we have the answer 3 and 4. Now you can ask me, here we are actually traveling 2 steps, right? So there must be a while loop. There must be a while loop to check, like if the previous one is 1, so we are moving then. So how is the complexity order of n? If you think about it carefully, think in terms of 2 pointers. The first pointer is traveling on the rows. It's order of n. The second pointer is always moving to the left. Is always moving to the left. So it is also irrespective of number of rows that we have. it will always move to the left and reach this end point. So it is also traveling a distance of order of n overall. So the total complexity is order of n plus n, which is order of n. So we can do it in order of n time. So order of n time, order of one space, because only 2 pointers are needed. Does this make sense? Is the logic clear with everyone? Is the logic clear with everyone? Is the logic clear with everyone? Sure. Time complexity. Okay. I'll explain the time complexity part again. Let's think about it, right? Let's think about it. We have 2 pointers, right? We have 2 pointers. The first pointer is moving in the rows, along the rows. The second pointer is moving across the columns. Now the first pointer is definitely moving across n rows, so it will be order of n. The first pointer complexity is order of n. Now for the second pointer, just think about it. The second pointer only moves towards the right. It will only move towards the left. It will not move back towards the right. So if it only moves towards the left, how many steps can it move overall? If it is moving towards the left, how many steps can it move overall? It can come here, it can then come here, it can then come here. After that, there is nowhere to go, right? So it can come overall, over all possible rows, it will overall come order of n steps only, because it is only moving towards the left in only one direction. So that's why the total complexity becomes what? First pointer complexity plus second pointer complexity. So this second pointer doesn't, like, although there are multiple rows and for every row it is moving some extent. But just think about it. I'll give an analogous example, right? Let's say you have an array. You have an array. In every move, you are removing some elements. In every move, you are removing some elements, right? So what is the complexity? Now it doesn't matter, right, how many elements you are moving in a single iteration. But overall, once you remove an element, you do not add it back. So how many elements are there to remove? N elements. So overall, for all possible iterations, you will remove at max n elements, right? So total complexity becomes order of n there. So similarly here also, it only moves to the left hand side. So it doesn't matter how many rows we are actually visiting. It can overall visit n columns. So that's why it is overall order of n. Now does it make sense? Does it make sense? Is the complexity clear with everyone? And space complexity, like, we just have 2 pointers, right? So that's order of 1. Okay. Let's look into the code. I believe that will make more sense, right? So let's look into the code for this. First, like, we have 2 pointers, right? So n plus n, because for the row pointer, that pointer that is moving on the rows, that is order of n total, because it is visiting n rows. The second n is because the second pointer that is moving along the columns. Now along the columns, it only moves towards the left hand side, so it can visit at max n columns over all possible rows. So the second pointer complexity is also order of n, so it's order of n plus order of n. Let's look into the code, right? So first is j equals to n. We'll start off at n, and int row equals to I, sorry, row equals to 0, and num once equals to 0 for now. So let's for the first row, let's determine. So for int I equals to 0, I less than n, I plus plus, right? I equals to 0, I less than n, I plus plus. If matrix of 0 I equals to 1, in that case we'll set j equals to I, and num ones equals to n minus I, and will break here, right? We'll break the loop here. This is done for the first row, right? First one we see, we set the j to be I, num ones is n minus I, and break. Now we'll move through all the rows, right, one by one. So for int I equals to 1, I less than n, I plus plus, right? Let's give some space here. I less than n, I plus plus. Now what do? We see if matrix of I j equals to 0, then the number of ones is definitely less, so we'll just continue. Otherwise, while j greater than 0 and matrix of I j minus 1 is equals to 1, we will do j minus minus and row equals to I, because this is becoming better, and num ones j equals to I, row equals to, okay, num ones equals to how much? N minus j. Num ones equals to n minus j, and we'll continue like this, right? So as long as that is happening, so we are done. So finally we'll return what? We'll return the row and num ones. That is what we'll return. So see, although there is a loop inside this, although there is a loop inside the row loop, right? Still it is overall order of n, because it is always going j minus minus, and we have a condition j greater than 0. So every time this loop is actually executed, j is decremented by 1, and j can at max go up to n. So that means this loop will be overall possible values of I, this loop will be executed n times only at max. Let's test. Output is 1 2. Let's submit and see if this is what. Okay, your output is 0 0, and we do have something better. 1 second. Okay, mat ij equals to 0. Now if j less than n, and let's add this condition and let's run this once again. This is because, like, if the first row doesn't have any ones, in that case it would actually point to n, right? So that's bad. So 2 3 is what we get, so I think that's correct. Okay, so it's also done. Let me know anyone has any doubts with the code. Now it's order of n complexity. I believe everyone has understood that, because although we have a loop inside, but this can at max visit n columns, right? It can at max visit n columns. So yeah, let me know if anyone has any. While j greater than 0, yes, no, that was not causing problem. This one was causing problem. Mat ij is 0, so initially it was set to n, right? So if the first row doesn't have any ones, it would actually check mat in, and this would always turn out to be true. So that's why it was actually giving problem. So the code is pretty simple, I believe. Let me know if you have any doubts with this. Anyone has any doubts with the code? like this is basically whatever we have discussed, we have just written that in code only. While j greater than 0, and if there are more number of ones, that is j minus 1 also has 1, in that case that's better, so we'll do j minus minus and we'll set that row to I, the best row, and we'll update our number of ones as well to n minus. Is it clear? Let me know if you have any problem here. Otherwise, like, we are done for the day. So just to remind you, if you don't know about this, I'm running a Amazon preparation series. So basically the idea being that when you actually are preparing for your interviews, let's say Amazon interviews, when you come to Geeks for Geeks, there are around 700 problems, right? So you are like clueless, how can you complete 700 problems or something, right? So that's why we have taken up a challenge that will, in 29 classes, not necessarily consecutive, I'll discuss about that, but in 29 classes we'll be solving 2 problems every day, and I'll be giving you 3 to 5 problems as homework. So approximately, like, after 29 days you are actually done with 150 problems, right? Approximately 150 problems. So that's a lot of problems. The first thing is, you are already done with 150 problems. That will definitely help. And not only 150 easy problem, 150 good problems, right? All the problems will be very good problems. So 150 problems. The second thing that's great here is that you are developing a practice as well. So when you actually, like, after we are done with 29 days, you can actually resume, continue with your practice, like solving 2 3 problems every day. So you will develop that habit of practicing, so that when you are actually sitting for interviews, you're already done with a lot of problems, so you don't have to, like, panic that time. So that's there. So we are running the series on Mondays, Wednesdays, and Fridays. The timing is generally 7:30 p.m. to 8:30 p.m., but again, that might be changed a bit based on my availability. So make sure, if you want to join there, you can join there as well. All right, that's all that I wanted to that I had today for you. So if you don't have any questions, we can end the stream here. Thank you guys for joining in, and I'll be seeing you, like, if you're joining tomorrow, so I'll be seeing you tomorrow. Otherwise, I'll be seeing you next Sunday. All right. No worries, Sagar. It was